Hi, I'm Alan Benjamin, the CEO at GigaIO Networks, where the network is finally the computer. I want to share a little bit with you today about the revolutionary things that we think we are bringing to interconnects in order to enable real rack scale servers and composable infrastructure. And tomorrow afternoon, one of our folks is going to give a presentation on the work that we have been doing with GPUs, and I encourage you to watch that as well. We believe that we represent the next step in computing infrastructure. Mainframes ultimately gave way to distributed computing in order to be able to scale. But the issue was, as it scaled, you were adding servers, and with each addition, you were adding redundant resources. With the emergence of accelerated compute and with specialized storage, you saw the rise of converged computing, where you could now create servers that had banks of GPUs or had large amounts of storage. But now the issue has become, as you put together systems with this, you strand those resources. And so we believe the next step is composable disaggregated infrastructure, where we can fully utilize all of the resources you're putting in the network. The waste associated with converged architectures is actually quite well known. This is a quote from Intel, but in the last 120 days, I have seen almost identical quotes from Dell, from IDC, from the Next platform, and from Forrester Research. The solution to this stranded resource is to be able to disaggregate, where you can create pools of resources, of storage, and of CPUs, and of memory, and of accelerators, all that can be shared as needed. The issue until now with disaggregation is best summarized by one of our potential customers who told me, as wonderful as disaggregation can be, it is useless unless you can re-aggregate these pieces without getting killed in performance, something we have not been able to do thus far. Now, of course, I'm not going to share that comment unless we can provide the answer. And so here you can see that in this example with GPUs, that GPUs composed across fabrics compare identically to those running inside of the server themselves. And even when you get to higher numbers, we do quite a bit better. Scott is going to share a lot more information on just this use case tomorrow. In order to be able to deliver rack scale cloud class composition, it requires a couple of pieces. First, you need to be able to compose resources to individual servers and then be able to move those resources to other servers as needed. This minimizes TCO and it improves serviceability and upgradability. Then we combine that with our ability to do internode communication or server-to-server communication, such as NVMe OF or GPU Direct RDMA, libfabric, MPI, TCP, to deliver scale and to ensure an easy integration with your existing operations. And we do all of this across one PCIe network with PCIe performance and industry-leading latency. It is this ability to not only attach resources, but to connect servers together to create a fully routable network that runs across PCI that is really the magic that FabreX brings. And all of it gives you sub-microsecond latency, whether you're running server to server or whether you're running resource to server. So let's take a quick look at how people use FabreX and put together networks. So first, people attach application servers with PCIe connections to our top of rack switch. And in some cases, they will stop right here and they will enjoy the latency and bandwidth advantages of running across PCI Gen 3 and or Gen 4 today. But some people will move on and add just a bunch of flash, a JBOF. And in this case, there is no server component in here at all. And you can compose this resource to any of the servers that are up above. And so you have a block of storage and you can attach it to a server, use it, move it to other servers. But we can also run NVMe-OF because we do internode communication. And you can connect to a storage server. In this case, you can run this as an NVMe-OF target. The application servers are the NVMe-OF initiators, and you have really very fine grain granularity over the storage that's in the storage server, and you can share it amongst all your application servers at the same time. And what we do with storage, we can do with GPUs. So we can either attach just a bunch of GPUs in a JBOG and move it between servers, or we can attach to GPU servers and allow the application servers to be able to use the GPUs in these server or servers. And it really can be just a bunch of anything. Anything that fits into a PCI slot will work well with FabreX. So it can be different kinds of GPUs. It can be FPGAs. It can be a 3D crosspoint. It can be custom chips of various types. And because PCI at its heart is a memory semantic network, you can actually do loads and stores directly across FabreX, and so you can create shared memory pools. So let's take a look at where the performance advantages of FabreX are really important today and where they're not as much right now. So with NAND SSDs, where you have latencies that are in the 50 to 80 microseconds, and Ethernet and InfiniBand have improved to 10 to 20 microseconds of transport latency, this is good enough. And for a lot of use cases, SSDs run fine over existing networks with NVMe-OF over those networks. On the other hand, as next generation storage comes around, things like ZNAND and even more so 3D Crosspoint, where latencies are in the 10 microsecond range, then obviously adding 10 to 20 microseconds of network transport on top of that is a problem, because you effectively get rid of the advantages of having such a fast medium. Today, NVMe-OF across FabreX runs at about 2.5 microseconds, and so if you're adding these faster storage type devices, it actually runs extremely well. And we believe this 2.5, we're going to get down to 1 or lower, and so as storage gets faster and faster, it's going to be absolutely necessary to get the kind of performance that we can get across FabreX. And obviously, GPUs and FPGAs are even faster yet, and so you need this kind of performance. The future is clearly moving to workflow-centric architectures. So take artificial intelligence, for example, where a given job may actually be a string of 5 or 6 different components, maybe a CNN feeding into a DNN, etc. And so you have containers that are working across a number of servers, and they want to work off of a common storage. And coming out of the storage, they may want to take advantage of multiple FPGAs for security or encryption, decryption, etc. And they want to feed into not just a bank of GPUs, but different kinds of GPUs for the job at hand. And so this ability to be able to really enable heterogeneous compute, the exact right processor for the job at hand, is really where FabreX excels. So that's a really brief introduction to some of the things that we're doing here at GigaIO and the problems that we are looking to solve. As I said, tomorrow afternoon, Scott Taylor, one of our folks, is going to be giving a much more detailed discussion about what we do with GPUs. And we look forward to having further discussion with any and all of you. Thank you very much.